So, friends, we are into our third lecture on operations management, risk management, and now we will be seeing management system, integrated operation management system. Most of the salient features of operation management system, when I say that aging management is also a part of operation, because aging management has become a very important and widespread tool, because people are able to enhance the life of the plant. I'll show you in the fifth lecture. So we will discuss many more features here also and there also. So in nutshell, the features that I am talking about, they are spread over all through this lecture, this module, and in previous module also. Okay, so let's start with the system. What I decided for developing this system, let us use a widely accepted core framework. So IAEA Tech Doc, in one of the IAEA Tech Doc, I have shown here 1141. It has been given that goal of nuclear power plant operational risk reduction. Okay, what should be the goal? So since I am adopting this framework, there are black things you will see and white thing you see. Black is our ARCOM introduction to clarify individual element of this framework, and white is what IAEA is saying about these goals. So like if we see from top what is required from a plant to perform safety, and then I'm translating that is low risk, and when I say low risk is either zero risk or risk acceptable risk. So this is a language, it has been used, but I am explicitly making it because I am dealing in risk domain. For me, the quantification comes here, because safety is cannot be quantified. Safety can be discussed in terms of improvement and adequate and reduction. So, but then here I am giving a quantified risk statement as part of the then the parameters that represent overall level of operational safety performance. So this is the second module. So this is the objective function. Then how we are doing it. So risk significant metrics. I am having the probability, I am having the core damage frequency, I am having the cut set conditional core damage frequencies, then and I have unavailability statements. So for me, again the quantified risk matrix, that is risk significant matrix, and then added to that I have for each component I have the importance measure. Fussell Wesley importance, risk reduction worth, risk achievement worth, all those things we have. So we can talk in those terms. So the first one was higher level of operational attributes that they will come here. So you can assume that this will be something like a matrix presented to the operator, wherein what we mean by risk. So core damage, or I have a risk monitor. So I will present what is the level of risk here, and for different system what are the unavailabilities they are there. So that will be and then risk significant matrix. That means I have a PRA, and again we are presenting to the operator how to achieve. This tells you how to achieve, go to this lowest risk level, and then the selector parameter and data model that represent operational safety. Now here we are talking about the reliability data, human factor data, hardware data, software data that we get over here, and then parameters that can be directly monitored and measured. And this is a control room scenario or site scenario where we are measuring the parameter, then any deviation occurs, then the performance comes into the picture, and that gets converted into a risk or safety, and finally how it is presented. So these are the, and so that means how to reach this goal of operational safety through basically data collection and operation ecosystem performance, then translating it into safety reliability data on human, hardware, software, and then finally core damage frequency, large this LERF is large early release frequency. It is the output of level 2 PSA. CDF, core damage frequency, is output of level 1 PSA. And overall risk matrix, I think I gave you an example of risk matrix also. How we develop likelihood, consequences, and then we have a reason where we have high risk red, we have medium risk amber, and then low risk green or something. So I think I have presented to you. I think you have to understand from there. Now, before we talk about the operation management system, I should know what are the major elements of operation. Okay, so you can see here that different functions have been shown. Let me put a disclaimer here that this may or may not be exhaustive. So I have indicated it. There could be many more functions. Or there can, in some metrics there may not be few. There may be few system. Others may not be there. But my almost like 35 years of experience in nuclear plant operations, and probably I feel it has been optimally designed, this matrix. So though operation is at the core of operation managed ecosystem, but the supporting systems are there which interface with the operation, but they have their identity individually also, like engineering, design, modification, and planning. So here this element, when I talk about the connotation of risk, I will say risk based design, and then evaluation of modification, its impact using the risk algorithm, and planning, prioritization, identification. So everywhere I can translate this matrix into risk domain, and then that means mathematical domain to be more appropriate. Staffing requirements, training and qualification, its evaluation, maintenance, testing and all. So how much maintenance is contributing to the plant availability, or trips and all that. So that can be evaluated. Development, update of checklist. Checklist means we are interfacing with the human factor. So whether the human have been given the right checklist, or are we modifying or updating it all across. So and then documentation, design, operation manual, procedure, technical specification, in service. There are many documents that are there, and then the operation documents, the operation safety and reliability. Operational safety, we have one document, technical specification, and then finally periodic reports that are issued. There are indicators in the operational document that shows what is the reliability, that is how many number of trips, what was the availability factor, capacity factor. So those get surveillance, supervision, what are the incident that has happened in the plant where close surveillance was required and supervision was needed more. So all those event reports, condition. So I can go on talking. Fuel handling is a special aspect of in nuclear sector. So it requires a sort of independent crew to perform fueling, because this itself is a task, or sometimes people do in part time also. Part time is not exactly, they are rotated from control room to fueling to control room, something like that, once in a year or once in 6 months. Data logging, reporting, radiation protection. Radiation protection is basically, it is meant, agencies are meant for hazard control and measurement of radiation aspects, and waste transport and management. Maintenance, we have the maintenance frequency, maintenance crew, human factor, periodic maintenance, retrofit, and inventory management. I think we saw inventory management as part of operation research, how we can improve the inventory management. One more, queuing theory or something, we will talk about decision making and all, one topic. And then test and maintenance. Then safety analysis, technical specification component, emergency drill, quality audit. These are various factors of operation. So, and the security aspects, physical security and cyber security aspect. So, these are the individual elements, and these elements invite us to work if you have any approach where the better algorithm can be developed, better mathematics can be developed, and an optimum solution can be achieved without compromising safety. Okay, and if that might result into enhanced reliability, that takes a lot of weightage actually. Okay, so what are the major element for implementation of integrated IRM system? So, if we talk about the plant basic attributes is deliverable. Like if I have to talk about space system, or if I have to talk about aviation systems, how many trips an aircraft had and what kind of maintenance it required, and then what are its operating domain. So, for like aviation is the dynamic domain. For plant on ground, they are citing thing, safety features, operation feature period, aging status, location and exclusion zone. These are the basic attributes, and PRA in general and level 1 PRA is particularly used in effective framework for operational risk management system. Risk based model basically it deals with the application area of the plant. Okay, and then risk conscious integrated operation management, monitoring, surveillance and operation. We tighten this, so we get into this, get data into this, and then model is developed, and again it operates in a closed loop actually. So, what are the, so now if I have to talk about major elements, what are the major elements? So, major element of integrated operation risk management is first identify. That means identify means develop a definition, okay, what you want, and then evaluate it. Evaluate it, it could be quantitative or qualitative, and once you evaluate at one level, then a complete assessment has to be done considering various parameters, prioritize, then assess the impact, corrective implementation, monitoring, and then feedback and monitoring is very important, and then quality audit assurance program on this, and documentation, and then again it ends here, and this feedback monitoring depending on the time, how long it can go and all. So, I will use, like I can say identify, evaluate and assessment into one sheet, but I will dedicate prioritization because some techniques we are talking about it. Impact assessment will be doing sensitivity analysis, and corrective action is a implementable feature. I mean, there is not discussion. Corrective, it could be making the system redundancy can be increased, or it can be adding a quantity sufficient for a certain mission period, or so we cannot go into the nitty gritty of what corrective actions you implemented. But when I talk about the aging study, I will be coming to these aspects. I will touch upon these aspects. I cannot say this. So, now identification and evaluation and assessment, they can happen at the level of brainstorming to begin with, and then they can have some sort of a systematic safety document, deterministic and probabilistic document development, and whether it is anything change, let us talk in terms of change, whether the change can be implemented or not implemented, a decision can be taken, and then finally it is a system level, like let us revisit our PRA model. I am assuming that PRA model, probabilistic risk assessment model, is available in the plant, and then finally we go to the so this once we map it on PRA and some more information collection, and then finally we have to talk about designing a tool, gadgets or methods or systems or subsystems for implementing the corrective thing. But before that, this particular so far what we have done, it will not give me a prioritized list of if I have some n number of jobs. So, I have to, I said identify and prioritize and evaluation. So, what will happen is prioritization has been done, and this is a, again we go back to our at the plant level, it is a, suppose if that change that we are reflecting, it was in let us say some system on any of the safety system. So, and those safety systems are related to loss of offside power initiating event. So we will choose this event tree and see what is the core damage frequency, and then we will come to the fault tree level and we will say, let us say it was related to emergency power. Let me, the modification was related to power supply. So we had two diesel generators, three diesel generators here, and there is a common cause thing also. So was the modification related to common cause? So the rank. So what will happen is, when we do visit the PRA model, we have to see the spectrum of that modification for normal operation as well as accident condition. Okay. Since we are talking about here, it is a anticipated operational occurrence. It keeps happening. Happening means once in a year, or once in 2 years, or it could be even once in 6 months also. It has not entered into the accident domain. Accident, this particular thing is not become reality, cut sets, So, but then when I do a change, I have to see how the effect is going to be. Normal operation. So this is normal operation, accident condition. Normal operation is normal plant operating at rated capacity or even some lower capacity, and anticipated operational occurrence also comes. So this is an anticipated operational occurrence, loss of offside power, and design extension condition, design basis accident. All the plants are designed for certain condition, and now this new paradigm beyond design basis accident, server severe accident and severe accident. So earlier it was a design basis accident, beyond design basis accident. Now it is a basis accident and severe accident condition. So has been added. So that becomes the area of accident condition, and then we'll see whether the kind redundancy we want to increase with 3DG to 4DG, or we were trying to fight out one common cause factor, environmental factor. It could be some common component, or it could be some human factor. So what factor we were looking for, and accordingly will reflect the change over there. And one good thing about the PRA framework is it produces a list of prioritized component, that is priority list based on importance, risk importance of the component. So we have discussed this and we will be discussing about it. So now we have to prioritize. Importance measures are available for each component, and how it is evaluated, that also we will see. So now we will be having a list of n number of components, which will start at the highest, having components or systems or cut sets having highest importance to lowest importance. So probably if we have to see which are the modification to be done, which are not the modification to be done, then we can use that list. So here we are seeing the importance, and then importance measure in failure space. Of course, we do not talk about the reliability, and we talk about the Fussell-Basely importance. Mostly applicable are risk achievement worth and risk reduction worth. Both are operating in the failure domain only, or it has been translated into the failure domain. Objective is the minimal cut set obtained from PRA is evaluated for the risk importance measure. Scope, the discussion will be limited to risk importance measure only, and common cause failure. Well, so this is a very important observation. The cut sets are made out of 2 or 3 component failure. It could one of the component could be human failure also. But common cause failures, single common cause failure, and what is the characteristic of common cause failure? One particular event affecting all the redundant system in adverse manner. Like 3 DGs will fail in one shot, and when power supply failure happens, none of the DG will start. So common cause failure DG is the most important thing, and as far as importance measures are concerned, it will come on top. You do not require any mathematics, and even if we do the analysis, that will come on top actually. Okay. So we have this. Now importance measure we have estimated. How we measure that? So importance measure for a component is a function of unavailability of the change in unavailability divided by change in system unavailability actually. So these two are related actually. Okay. So importance measure, risk importance measure is the amount. Yeah, I am just explaining it. Now how importance measure varies? Location of the component, where it is placed, configuration, series and parallel. If a component, if suppose some function is there, diesel generator, let us say, if we have provided one diesel generator and it is in series, okay, system, series system, one breaker, diesel generator, and again breaker, and then input output. Importance of diesel generators will be very high. Why? Because there is no other system which can make up for this system if it fails. But suppose if we have two diesel generators, importance of diesel generator, individual diesel generator in parallel configuration will be lower. So that's how we see. And then failure probability. So these two, especially these two together, they decide the importance measure of the component, because finally we are talking about unavailability. So that will depend on the component configuration. The above is analyzed at system level in PRA, employing fault tree and minimal cut set at plant level. Now we'll discuss one of the Fussell-Wesley importance measure. What it says, at system level, the Fussell-Wesley importance measure component is so for ith component, if we are talking about, so availability of the ith component and then system unavailability, the fraction of these two will give us the importance of this component. Okay. The model facilitates estimation of component risk importance, and once components are arranged according to their importance, we have a list of prioritized component risk with risk significance or risk impact, and that can be used to prioritize operational maintenance test. A simple example is there. If we have a problem in maintenance, that which components are more important? Obviously, safety important component, but among safety safety support or safety system component, which are more important? If we have to arrange a list, so we can do a system level modeling, and we can understand the key which is coming on top. It will be governed by its position and its failure probability. Okay. If the failure probability was more and unavailability was more, then it will rank very high. So, these models, they give a rational based methods, rational based approach, and unless until data change, it will not change. So this is how it is science based approach we can say. At plant level, if we have something, so what is going to happen at the plant level? List of cut sets we have been given, and then in that, see, for ith cut set, the Fussell-Wesley importance. So I is a function of time, and then it is at system level also it is a function of time. So list of cut set along with the frequency of occurrence obtained from PRA to arrive at the. So what is the cut set frequency we have here? What is the cut set frequency we have here as this thing? And then now at system level and at the individual level, and then we can estimate the importance measure here. Now for a cut set at the plant level, if you have to do, then there are two directly. Now we are talking in terms of language of probabilistic risk assessment, because probabilistic risk assessment gives us the core damage frequency. So what is the plant core damage frequency, and what is the plant core damage frequency when unavailability is set to 0. So here we are talking about the component which has the lowest, almost approaching 0. Okay. So what we will get? Risk reduction worth. Risk will reduce because unavailability we have made almost 0. Okay, or 0. So we will get risk reduction worth of the component. This is the importance measure, and the list will based on this. It is very intimately connected to the PRA modeling. Second one is risk achievement worth. Risk achievement means that component value has been set to 1, and then core damage frequency of the plant, what we will get, and CDP, overall core damage frequency we have actually. So these are the measures with very elegant measures that are available, which are not subjective unless until the data changes or some configuration has been changed. These factors will not change, and they are very valuable tools for identification and prioritization of the component as part of risk. Now, other aspect of the RCOM culture is impact assessment. Impact assessment, generally it becomes part of PSA or any change report that is being prepared, because everything we don't know in the plant or change where we are impacting. Sometimes data is not available, sometimes we don't know what to do or how to replace this component, so data and information is very important, but then the job has to be done. So how we do it? We assume some data. Suppose new component has arrived in the plant. I do not have data. I might talk to the vendor and he might give some input. But then his input could be conservative or very optimistic also. So we have to weigh it and accordingly we have to use. But then finally I have to see the impact of this particular data or information at the output level, how it has impacted my assessment or evaluation model. And similarly, some events because the knowledge is not there, we undeveloped events we have, and we assign some value. So on those nodes. So how my final results vary. So that's why we call for assessment of assumptions, postulations. We use what are their impact on overall results of the plant, and then only decision can be taken. A change made in the plant configuration that might involve increase in redundancy, use of diverse mode of operations, So how much it is increasing, that assessment has to be there. Presentation of final results. So this impact assessment becomes part and parcel of discussion when we present the result, and then the analyst has to make explicitly clear the final results being presented considering these assumptions, and these are the decisions, and that's how it is available to anybody and everybody to analyze. Suppose if I have done a risk assessment, I have not included the seismic component of the risk, and then what I do, I don't have a risk seismic data with me. I'll go and survey and I'll see what is the range of seismic impact from other studies, and I'll use that range, maximum and minimum, and I'll demonstrate where is my plant's risk. Otherwise, performing a seismic risk assessment might become prohibitive because data is not available, or even if it is available, it is very low. So these are something, management techniques, but it should be made clear what are the impacts of these data or situation on the final result of the problem. And then corrective action. See, in any changes, the recommendations are made. Again, we'll discuss about it when we discuss the aging management of one isomate plant, which was done. So recommendation can be like in the form of you replace this component, recondition this component, but sometimes it is not possible to change anything like passive components, structures. So what kind of reconditioning should be done, or how far they can. So then the qualification criteria becomes very important. Some samples are collected and all. So there are different techniques for corrective action program, so that my purpose is met. If my purpose was life extension, it is done. My purpose was to increase or reduce the risk, that is met. My purpose was to see how redundancy is adequate or not, or I have to go for some retrofit, those things are done. So these are, and then the analyst, once job is over, then it can be subjected to independent review, it can be subjected to regulatory review, and then only decision can be taken about repair and replacement, because sometime all these exercises, they are very, very resource intensive. Systems have to be designed, and then it has to be tested, and most important, the corrected section system should not bring in a new element of risk or deterioration in reliability. That has to be seen. It should not interfere with that. Then once the study is completed, quality control measures, all for modification, for PRA, for system selection, for procedures that we are evaluating, everywhere quality level should be there, and if they are standard available, use those standards. Otherwise, we'll have to develop our own quality standards and perform, and we have to demonstrate that these are our quality specification for these jobs. Now it is for somebody to accept or reject, or at least ask for some improvement, so that can be done actually.